I'm gonna really one of the
没有，他们就3天Oh, I see. Their assignment.
Yeah. This is important. That's right.
You think you're leaving him out for a second? No, you like the school last time?
Like that.
Then it's okay. I think that's
Now it's not now the meaning like it's not like it's
smaller one size.
days, 5 more I just
Less than 2 weeks now.
I don't know, like, if we've been talking to drive, right? I don't know, like, do that.
Now,
To be stupid.
I said, I just don't know where we get to finish. The M question, right? I was saying something right to me. Good afternoon, everyone.
I didn't use
Welcome to the last seminar
like from
of the term.
the model.
Yay! Last seminar of the term. See you again in a month and a half. Of course not. Today we have our very own Professor Hanping, who's been with us for 26 years now. So really exciting to hear some of the work that he's been working on recently. Please.
Thank you very much. I was expecting more people so I can see. So let's start. Today I'm going to talk about something that I was working with my graduate student, the former and the present, and actually the project is funded by Natural Research Council of Canada and Canadian Association. So for those of you that received your education in Canada undergraduate, you know there are two design codes that you must use, or at least one of them, National Building Code of Canada. Another one that is important is CHBDC or CSAS6, which is for Canadian Highway Bridge Design Codes. Okay, when I was a student a long time ago, I was graduate student, long time ago. I was thinking the codes are made by a bunch of old guys sitting in a room and open a bottle of cognac, the pipes in the hand and the smoke pipe, and it says, we should put the 1.25 for that load and the 1.4 for whatever load, and that's it. As I grow older and starting doing these kind of things, I find that that's not actually the case. Each of the sentences in your design code sometimes takes about the whole day, and the 50 old guys, most of them are old guys, sitting there and debating. And at the end of the day, perhaps they come up to the conclusion the statement is right or wrong, needed to be revised. But imagine the whole day just for one sentence. So today I'm going to tell you the process of calibration, the load factors for wind, snow, and ice for National Building Code of Canada. Okay, it involves a few things about the statistics, which I'm sure many of you like very much since the second year of your university or even before that and high school, okay? And trying to reduce the mass to minimum, okay? So just to make things a little bit more interesting instead of pure mass. Okay, so what is design code? What is the objective? So the objective of design code is to limit the probability that a person in or adjacent to the building will be exposed to an unacceptable risk of injury due to structure failure. This is quoted sentence from the National Building Code of Canada. There are some objectives to prevent loads exceeding capacity of building element or supporting medium, damage, the deterioration of elements, so you need to prevent the vibration or deflection of elements, and prevent the instability of building or part of building, prevent collapse of excavation. National building codes most often are focused on structures, or loading focused on structures rather than foundation. I think the new version of NBCC 2025 will include many more things related to foundation. I'm going to only talk about the structure part, and remember that we are often talking about the structure element rather than the structure system, because this structure system is much more complicated than a structure element. Okay, so key point for calibrating a design code are three. You need to identify limit state function. So what is the limit state? Capacity versus demand, resistance of a structure member versus load effects on a structure member. That's limit state, okay? We need to select a selection of assignment of probability models of random variables. In other words, we need to say the distribution of a random variable. For example, wind speed, how it is distributed. We cannot precisely predict the extreme wind during the year. So we must somehow get in data and assign the distribution. The third task in the design code calibration is we need to set an objective. Okay? What is the objective? Objective is a reliability index or tolerable failure probability. A long time ago, one of my colleagues corrected me. I cannot say target failure probability. We are not targeted for failure. We getting a tolerable failure probability. An illustration of those three are shown in here. You have factory design load less or equal to factory design resistance, R being resistance, L being load. And you can think about this curve represents the load effects and this represents resistance. When you pull these two curves away from each other, the failure probability decreases. When you get these two close to each other, the failure probability increases. For example, if the green one falls at the center of the red one, so coincide, then the chance of failure is 50-50. You do not want to live in a house with chance of failure of 50%. I'm sure, I bet you don't want. Okay? I will not. So the idea is that you need to calculate the probability of failure. In other words, Z, resistance minus load less or equal to 0. You try to adjust the specified load effects, which is represented by this value. You try to adjust the specified resistance, which is represented by this value. Perhaps you need to times a factor for load effects and times a resistance factor for these resistance, nominal resistance, such that this condition is satisfied at minimal requirement. So again, those are two curves. How to calculate this probability of failure is something a little bit more scary. If it says load and the resistance factor is defined, resistance is defined by this limited state function, and the chance of failure, okay, chance of failure, if they are normally distributed, you can express this way. This represents mean of resistance, mean of load effects, standard deviation of resistance, standard deviation of load effects. Beta is known as reliability index. Nothing is that easy in life. So sometimes you have something called log normally distributed random variable. In case you have log normally distributed load, resistance, and the load effects, the reliability index can be calculated approximately by this equation. And one of the things you observe is that the reliability or safety of your structure is controlled by the coefficient of variation of load effects. That's important. Of course, it is controlled by R, mean value, and the mean value. Mean value, we have better control, perhaps. The coefficient of variation, we don't know how to deal with it, and we need to figure out. This plot shows a more sophisticated approach to calculate the chance of failure. Okay, so details of that I will not talk about. Essentially, what you are doing is you have a limited state function. You are in a space which is not normal, and you map to normal space. Okay, so you standard normal space, and in standard normal space, you figure out the distance called beta, reliability index, and using that as a measure for the reliability. As long as we kind of understand this beta, then we are okay. If you do not like the way of thinking analytically, you can think about as follows, that you have dead load, you have dead load renovation, so you dead load changes. On top of that, you have sustained live load. On top of that, you have snow load, and you have change in the live and the wind load. You put all of them together, and you repeat this process for a long time, let's say 50 years. and go it again and again and again, and you figure out what the chance of exceeding maximal design level or exceeding a specified resistance. You do this using something called Monte Carlo technique. We are not gambling, okay? So this is simply a numerical exercise to figure out what is the chance of failure. And for example, the old called MBCC, the calibration was carried out by Bartlett, Hong, and Dr. Joe. And that was implemented, I think, in 2005 about the load factors. The process of calculating these, there is a lot of mathematics, and one of them is called Poisson-Force process, and this is shown in here. So you need a mathematical model to do the simulation, and once you done simulation, you can calculate what the chance of failure. Okay, so now let's focus on the limited state function that with bunch of random variables, that dead law, live law, wind law, earthquake law, and so on and so forth. Design requirement is anyway the factory resistance must be large than equal to factory load. The third thing we says for carry out reliability based calibration is target reliability index. In here, we have target reliability index. It says 3.5 and corresponding failure probability. When we translate in that, we need to consider that the dead law remains constant during service period. So in a sense, the annual probability failure, in other words, first year, second year, third year, they are partially correlated because dead law remains the same, although it's unknown. The translation of 30 years to 50 years, you have 3.5 becomes 3.36. So roughly, the reliability index of 3.0 is used for National Building Code of Canada calibration. For bridge design code is slightly different. It's 3.5 for 75 years, okay? Now, you may ask this, the structure fine, why you are doing all those crazy stuff? They are observed damages. And this one is one that happened in this year, killed only 11 people. It's a lot. I will say only because just to call your attention, it's horrible, okay? And the damage cost is 780 million USD. I did not do that. I just copied from Watch News, and the pictures are collected from websites. So Terrico is a kind of like a huge downburst. In other words, is cold air come down from the sky, touch the ground and move forward, and the system moves on. This particular Terrico affected many locations, including our own city and up to Quebec City. Ice storm will affect our infrastructure, and here was collected by Dr. Zhang, who in one of the presentations showed all these interesting pictures showing collapse of transmission tower due to ice storm. Snow can cause collapse of buildings. So there are examples showing collapse of buildings, collapse of transmission towers, and so on and so forth, due to ice, due to snow, due to wind. Okay, ice is most important for transmission tower. So now let's think about how can we do and whether the design code is adequate enough. If not, should we revise it we know that if you have tons of money, you can build your house very safe. Even there is a huge tornado, 5 comes, nothing will happen. But the design is balance of economics and the safety. So we need first to understand the uncertainty of wind loading, uncertainty of snow loading, uncertainty of ice loading. To do that, the first thing is getting the data. So reliability analysis or statistic analysis for civil engineering, the first thing is data, second thing is data, third thing is data. If you have enough data, everything can be done. And if you are following the large data or data science, if you have sufficient data, you don't need to know almost math. You use an algorithm to figure out things. But here we have limited data. So the number of stations that contain minimum of 10 years of usable data is reduced. In this case, this give DYL is a daily data. In other words, you have only one data point for each station during a day. You can also have data, so HYL01 is hourly data, and these are the stations. Usually it's more than 250 stations that have sufficient data you can use, because we want to carry out extreme value analysis, and we need at least 20 years of usable data. Without such, there is a huge uncertainty, okay? Huge uncertainty in the assigned distribution for wind speed. We carry out a statistical analysis, and this just shows the trend for the mean wind speed and the coefficient of variation of mean wind speed. As you can see, the coefficient of variation vary from location to location. So extreme 0.05 to about 0.3. And we mentioned that the reliability index is kind of depends on what is coefficient of variation. We also identify the thunderstorm winds versus non-thunderstorm winds. The reason is that they belongs to different population. What the heck is population? So there are two different animals for that. Okay. And we carry out the analysis. We says 50-year return period is shown here. Okay. And the 500-year return period, the value of wind speed is shown in here. What is 50-year return period? What is 500-year return period? Essentially, 50-year return period is the chance of the wind speed that you observe in a year higher than that value is 1 divided by 50. So 0.02% per year. And 500 years, the chance of exceeding it is 0.2% per year. That's roughly it. We also like to see this kind of maps. We don't want to be experienced these kind of things. And this is only, I believe, only a 5 tornado that has been observed in Canada and happened in Ely, Manitoba. Now, the statistics of tornadoes are shown in here. So there are a lot of tornadoes, in a sense, less than US, but there is a lot of tornadoes. Why we are interested in that? There are a couple of things. Tornado catalog is incomplete because Canada is huge, and some places you may not have people living in there. They may have tornadoes, and we need to figure out whether there is or there isn't, using some kind of parameter, other parameter that give us an indication. One of them is number of days that have thunderstorm, and the other thing is lightning. We include in the thunderstorm days and the lightning data to evaluate the occurrence of tornado. So the summary is that if you are living in this area, which are red, the tornado occurrence is higher. So these yellow and green, less and less. So you move towards north, there's no tornado. If you ask me whether in the future there will be more tornado due to climate change, I will say I simply don't know. Okay, perhaps because the warming temperature move some of the tornado or systems to Canada from the US, perhaps increase, but I do not know. Okay, those are based on historical data. For those who are working in wind engineering, we say, by the way, the tornado wind profile along the height is different than synoptic wind. We are not using the wind profile for synoptic wind for tornado. So what that means? In other words, if you know at the 10-meter height wind speed and the wind speed along the height changes like this, if it's synoptic wind. Now, if you have tornado, the wind speed changes like this, depends on what is the return period you are using. And that is an equivalent tornado wind speed. So along height wind profile. The parameters are showing here is kind of empirical. So at least we know how the wind profile changes. These have implication for design if you wanted to use it. Think about it, you have wind speed at here where it's like this, and you have another one vertically. Of course, this will cause more shear and bending moment. We compare the hazard due to tornado wind and the regular wind, like synoptic and the thunderstorm wind. We find that these are much less than 500-year return period value of synoptic wind. One may therefore think that the wind has some from left to right is tornado, wind has some F. So what we can say is tornado is not important for Canada, but there's a caveat to that. First of all, the center of low atmospheric pressure was not considered in this one or this one, this one. So there's a suction that suck your roof up. Okay. Those who are interested can go to consult a paper by Dr. Kopp and the Wu, which is very interesting in dealing with tornado wind loading. Second, tornado wind hazard could dominate as the footprint area or infrastructure system. So what we are saying is that as your footprint increases, the chance being hit by a tornado increases. You say, I do not need to do any research. I know that will be the case. But for sure, you need to do numerical analysis to know how much increase. So if it's a diameter of 100 meters, the area, the striking rate is double. If you have a line of 10 kilometer long transmission line, the order of hazard is about 1 to 2 order of magnitude. In other words, exceeding a specific wind speed, let's say for 1 point is 10 minus 3, 10 minus 5. If you consider 10 kilometers, such exceedance perhaps 10 minus 3. So the risk is much, much higher, or hazard is much higher. Okay. There is one more thing that the ASCE 722 consider tornado winds for design. In Canada, we don't consider. So it's likely all these things will impact future Canadian design code. When I say future Canadian design code, I'm not talking about the 2025. It's too late. They're working about 5 years, and at the middle of the 5 year, everything needed to be done. Public consultation, voting, democratic process, and so on and so forth. And then the code will come out. So if you are working on things about the 2030, now you need to speed up and trying to get things in 5 years and for discussion. Okay, snow load. So just to show you the snow load map, and one of the things that I wanted to show is coefficient of variation varies much more significantly. That's ground snow depths. The depth alone does not give us loading. The depth times snow pack bulk density give us the weight, give us the ground snow load. Okay, and the mapping of these is usually carried out using something called cribbing. Okay, just the spatial smoothing. And as you can see, the 50, 500 year and the 1,000 year map I show as in here. The density, the snow bulk density is showing here, and there are several zones, different zones have this different weight. For example, if you go to Vancouver, the snow is wet, is heavy. And I think if you go to Edmonton, the snow is very fluffy, very nice. And I understand if Chinook comes, the snow will disappear in Calgary. Okay, just eaten by the wind. By combining the snow depths, annual maximum, and the snow bulk density, and we have the maps shown in here, the ground snow load. I must emphasize ground snow load is different than the snow load on the roof of your house. There is a transmission or transformation from ground snow to the roof because of exposure and the wind and so on and so forth. So that needed to take into account. Ice, we have ice aggression. So you have freezing rain and so on. You need to do extreme value analysis and getting the map. And this map shows you the spatial trend of the ice aggression. And ice could be a problem for bridges or sign supporting structures. One of the things I wanted to mention is that in Canada, okay, Gumbel distribution is often used. In US, they use generalized Pareto model. And we found that the log normal perhaps even is simpler and better, but it's still debatable which one to use. The code committee says the Gumbel should be used because of tradition. So this shows the variation of ice thickness. And as you can see, this area ice than east, so colder and warmer. This comparison of existing ice thickness in S6, which is bridge design code, and C22.3, which is for transmission lines. Okay. What we obtained is slightly different than what is shown in the design code. And it's debatable which one is preferred. And this needs to be further discussed. Okay. Now we identified the models for the environmental load parameters. Now we need to identify the limit state function or load combination in National Building Code of Canada, and trying to see what is the reliability. The calibration of those things, which are included here, you can find in the paper by Bartlett, Hong, and Joe, I think in 2003. There were two interesting papers. All the statistics that used for resistance are still used, and the load effects perhaps change slightly. The point that I wanted to make is that plus live, that plus wind, that plus snow, no matter which one you use, following the code is about 3. Target reliability is about 3, and it's achieved. It's okay. So higher, a little bit higher, it's okay. So this confirms as long as you use typical coefficient of variation, everything is fine. However, if you are using the coefficient of variation of wind speed from 0.05 to 0.3, which is the range for Canada, you will find out this probability of failure is about 2 orders of magnitude difference. It's huge. And this is based on 50-year return period and 1.4 of wind load factor. However, if you use a 500-year return period of value with load factor 1.0, this range is much narrower, and the difference between the failure probability is within order of magnitude. So the story is that if you using the existing code, if you are designing for Vancouver or designing for, I don't know, or for Halifax, the chance of failure will be significantly different. For locations, maybe up to 2 orders of magnitude difference. If you're using the new format, the difference perhaps is less than an order of magnitude. So it's drastically reduced. And hence the reliability consistency. Now, this project did not stop in using historic data. We need to move on with climate change. And the climate scientists tell us, depends on the representative concentration pathway, you may get something like this for the temperature change, or something like this, depends on which scenario you are using. So RCP 2.6 and 8.5 are often considered. The meaning of 2.6 and 8.5 is that after a possible range of radiative forcing value in the year 2100, 2.6 or 8.5 watts per meter squared. That's what it's trying to say. But for us civil engineer, we know those climatologists tell us likely scenario will be 8.5 or 2.6. We just adopt it and use it. Okay. Cano and others carried out significant analysis using many of the climate models and concluded a few things for Canada that are interesting to us. First of all, if RCP is 8.5, okay, so temperature increase, you can get it versus time increment since 2000. And this is the temperature change for Canada. Once you have that, you can have change in the mean of annual maximum wind speed. You have change in the COV, coefficient of variation of maximum wind speed. You consider this, you say, I still want the target reliability index T50 to be 3. What is the adjustment factor for the wind load? And it is safe to say less than 1.07. However, if you say at any given year, my reliability index should satisfy a minimum that is what observed now without climate change, this value ranges from, about 1.02 to 1.12 roughly. So we come to the conclusion that a climate change scaling factor of 1.07 could be conservative for Canada. Now, whether this number or any other number is accepted is depending on the voting process. We, as researchers, we just provide the information to the code committee, explain what we find, and the code committee will vote or voice their thoughts and finally determine which one we should use. Okay, so the eta CW should be used in load combination or when wind load is the dominant loading. We carry out the same analysis using current design code and by considering a return period of 1,225 years for snow load. And these are the comparison of the reliability index. And we think instead of 1.5, 50-year return period 1.0, and as 1,225 years will be preferred. The 2% in 50 years, 4% in 50 years, not fair to do. Okay, and again, from Kano's report, what we obtain are those changes due to global warming. If you have global warming temperature, you know what is the change of coefficient of variation. Once we have those changes, we carry out reliability analysis and we figured out these are the values we need to adjust for the snow load. Depends on which objective you want to achieve. You want target in 50 years or you want them target at each year to at least satisfy this requirement. You may notice that in most places, the snow load will not increase but decrease. Of course, you can think about that. The temperature increases, there will be less snow. Consequently, the snow load is less. Okay. So the conclusion that we come up, or suggestion we come up, is as follows. So as climate scaling factor equal to 1 except for north, which is 1.05. So we are a little bit conservative. Now I'm going to move to CHB, this Highway Bridge Design Code. As you can see, Highway Bridge Design Code is that low, the load factor changes. It depends which component of that load that you are interested. Okay. Asphalt usually you cannot control very well, and that load parameter will increase. You have live load, wind load, ice loading. So ice loading is 1.3 load factor, and the combination factor is 0.75. There is a small print. I'm not going to read it. So if you are designing the bridge, you need to consider whether the bridge has a span longer than 125 meters or less than 125 meters. There is a debate where that number comes from. Simply says come out from a bunch of guys' head. Okay, there is no specific objective criteria to define 125, but that's set in design code. Again, for those who already took wind engineering courses or trained in wind engineering, you know this school is famous because this, or I should say, this department is famous partly because the later Professor Alan Davenport, who is considered the father of modern wind engineering. And according to him, the wind load is a wind load chain that you can define using gust spectrum, air admittance, air force spectrum, mechanical admittance, and the response. Okay. In terms of writing the equation, uses wind load is equal to analysis coefficient, exposure coefficient, gust factor, and the J coefficient. VT is the mean wind speed. One of the things that I should warn you is that do not mix US code with Canadian code. US code uses 3-second gust wind speed. Canadian code uses hourly mean wind speed. Either you use complete US code or Canadian code, but you use half of half, you will be getting into a lot of trouble. We carry out calibration. We says using a bunch of parameters define different short span bridges, and using current design code, this is the reliability index range. If I use a wind load of 1.0 and the wind speed of 500, this range is narrow, as shown here, and consequently, these values are suggested. It's understandable. So the wind load is 1.4. Take square root of 1.4 is about 1.2 something. You go up for a particular case of wind speed. I think this is the wrong one. Anyway, go up to the number distribution with coefficient of variation of 13.4 or 13.8. Come out roughly about 500 years. So this essentially justifies this is adequate. This I already showed to you due to climate change. That one of the issues that need to be worried about is in National Building Code Committee, it was decided or the committee voted 8.5 for RCP. But in Bridge Design Code, they voted 6.0. Why? They voted, okay, democratic process. They consider owners, operators, interest and public safety, and they believe this is adequate. So carry out the calibration, and again, in this, you get a scaling factor. Here, instead of beta, now we use alpha in here, but I'm going to change it later on. So again, for ice, we do the same. We can come up to values that take into account the climate change. So the revised suggested load factors that you need to use are as follows. As you can see, instead of 1.4, now it's 1, 1.3 is 1, and the load combination factor has been changed. The interesting thing is here that the wind load scaling factor 1.05 is suggested. A regional dependent ice load factor for British Columbia and Quebec, and so on and so forth. I must say some of this for Perry is still debating. The reason is that the data obtained from Environmental Canada define the Perry provinces as a single region. Perhaps it's better to define it as two regions. One is south, one is north. Okay, south is kind of warmer than the north. The 1.8, 80% increase sounds scary, but it's not that important. To begin with, there's ice thickness for, let's say, north of Manitoba, it's millimeters, 2 millimeters, 3 millimeters. You increase 80%, 6 millimeters. It's still very small, doesn't dominate. But for south, increase of 80% may be a concern. So we will take further scrutiny in this one. Okay, so I'm almost done. Okay, so to take home is as follows. Reliability analysis is not something that scary. It's just a manipulation of probability. You need to consider the target reliability index for design calibration for Canada, 3.0 for 50 years for National Building Code Canada. It's adopted before and we still use it. For bridge design, we use 3.5, but for 75 years, okay? You cannot use a reliability index for 1 year and says that's for 50 years. They're totally different anyway. It is shown that the use of load factor of 1.0 with the nominal loads defined based on ultimate written period is preferred for improved reliability consistency. So we are not crazy, okay? We are saying the wind load need to be defined based on 500-year return period. You think about it, it's 0.2% exceedance in every year. The reason we believe using 1.4 50 years is not adequate is in such a format you cannot take into account the spatially varying coefficient of variation. And using 1.0 500 year, for example, for wind would be better. Of course, we suggested for snow and ice loading as well. Extreme tornado wind acting on a structure with a small spatially distributed footprint is very low. So I often ask the question, if the tornado hazard for a single structure is so low, why should we worry about? Well, we are not only dealing with a single structure, sometimes we dealing with a structure complex or group of structures. As the footprints increases, for example, even 100 meter diameter, you increase the striking rate is about twice. And if you have a transmission line of just 10 kilometers, the chance of any point within the transmission line being hit by a tornado, the hazard is increased by 2 orders of magnitude. It's a lot, order of magnitude, so 100 times, 1 to 10 to 100 times. So that is important. So in other words, tornado wind load for a single structure may not need to be considered. However, this cannot be said for infrastructure with extended footprint, such as transmission line, building complex, or group of structures. So I emphasize again, this is not saying many of researches carried out in this university is useless. It's useful, except for single, if you are focused on single house, the risk is low. But if you're dealing with 100 kilometers of transmission line, then become dominant effects. So I showed the new sets of design loads and the load combinations, and some of these are currently under discussion. And you know, the discussion sometimes says yes, and don't forget what has discussed, they come back again, and so on and so forth. So this, I would say, still under discussion. But if changes happen, will be in 2025. Of course, 2020 code came out late, at least by 1 year. Commentary came out late for 2 years. So perhaps 2025 code will come out in 2026. I don't know. Okay. And based on the climate change effects and the reliability analysis, climate change scaling factor for wind load, snow load, ice load are recommended. I believe that such type of implementation is easy to deal with. You only consider a scaling factor, most often is about 5%. And the details are shown in the table. So the code will be the same format, except that the load factor changes slightly. Okay. I could not do all these by myself. I should attribute most of the results that carried out by former students and current students. And there are collaborations with other institutions and practitioners. I always needed to say this. Financial support from National Research Council, Environmental Canada, RWDI, and CSA, AE. I think AE is associated with Associated Engineers company. So all the financial support is highly appreciated. The more money, the better, of course. Thank you very much.
We have room for 1 or 2 questions? Yes.
For gathering weather data, have you considered using reanalysis data sets?
The analysis data sets, it's good. You know how. You guys know what is reanalysis data? Essentially, let's say you want to carry out the forecast of future weather. You have current weather. So after 6 hours, you want to know what's going on. So you collect all the information using your computer model to predict it roughly. That's reanalysis data. Reanalysis data, there are a couple of places you can obtain. One is used in Europe and another one in the US for sure. The reanalysis data is good. We compared some of them, for example, for Western Canada, and we find that they are very different than the recorded wind speed. Now, I know that you can use the analysis data trying to calculate the ice aggression, and that would be interesting to explore. In addition, some people try nowadays using the analysis data to identify whether there was some storm day or not. And all these will be interesting analysis. However, I believe the best thing is you will have good data on the surface records.
One last question. Anyone? Okay, well, let's give another round of thanks. Exit QR code today. So don't forget to scan that on the way up.